Hi everyone, this is your source of physical chemistry information, Dr. Hopkins. In today's video, we're going to continue discussing polyatomic molecules with respect to molecular structure. And so last time we did what would probably be the more complete way to describe the LCAM if we wanted to know everything about all of the potential molecular orbitals and bonding, etc. We would use computational techniques. We'd have to use some kind of program, particularly as we get larger molecules and so forth, in order to predict those molecular orbitals. What we're going to do in this video is describe a qualitative molecular orbital approach that centers only on electrons in pi bonds or electrons in delocalized pi bonding. And it's called Huckel theory, and actually there's a umlaut over the U, but I'm not going to pronounce it that way. So we're going to use an approximation based on Huckel theory, where we ignore all of the other atomic orbitals. So any of the sigma bonding, any of the non-bonding orbitals, we're going to ignore those. And we're just going to construct our MOs from whatever NPX, NPY, whichever one it is, it doesn't really matter, atomic orbitals that we need to construct these pi bonding regions. And so I show kind of the classical benzene where you have this delocalized pi bonding. Anyway, so let's look at the simplest pi bonding system, and that's ethene or ethylene, where you have a double bond between two carbons, right? And so we're just considering, so notice this is what? A total of 6 atoms, but we're only considering one bond. So this is kind of like H2 plus, right? So we're just considering that one pi bond. So it's like considering the H2 plus. So we construct the determinant just like we did with H2 plus, okay? Where the H11 and H22s are our Coulomb integrals, and we're going to substitute alpha in that for those. And remember, our H21 and H12 are our resonance integrals, and then any of our S's are overlap integrals, whereas where the S11, S22 are on the same atom, and so they're normalized, and those go to 1. So if we do that, we simplify this determinant to alpha minus E is on our diagonal, and on the off diagonal is the beta minus E times this overlap integral. Okay, so then we have that 2 by 2 determinant. We could solve that computationally, assuming that we can solve all the integrals associated with alpha, beta, and S. But rather what we're going to do is we're going to make the Huckel approximation. And so there are 3 kind of steps to this. All of our overlap integrals we're going to set to 0. Okay, so we're just going to say they're not close enough to have orbital overlap in these particular systems. All our resonance integrals between non-neighbors are equal to 0. So we're not going to let non-neighbors have interaction in that sense. And then all remaining resonance integrals, so those between neighbors, are just equal to beta. So they're all identical. Okay, and that should make some sense if what we're looking at are all carbons forming pi bonds. They should all be relatively the same. And so that further simplifies our 2 by 2 determinant to the diagonals are alpha minus E. The betas are on our off diagonal, so it'd be this minus this, which we can solve. And then we get 2 solutions where it's alpha plus or minus beta. Okay? And so the alpha plus beta, that's the attractive interaction. So those are both negative, so the attractive interaction. That's our lowest orbital, right? That's the one where we have the linear combination where there overlap between the two. And then the alpha minus beta is the one where there's nodes between the two. Here I've shown kind of using ChemDraw structures that I try to patch together here. And then our 2 electrons are in our bonding or this lowest energy MO. And so the total pi electron binding energy, is 2 times that alpha plus beta. Now, if we wanted to evaluate alpha and beta, those are integrals. Those are expectation values with the Hamiltonian, etc. So those aren't particularly easy to evaluate. But, so that would be the solution for ethylene. So let's go up to, say, butadiene. So let's take two pi bonds, right? And so at C4H6, we're going to have 4 pi electrons, one for each carbon, because they're just 2 double bonds. And then we would write our determinant with all of the Huckel approximation applied. So I'm not writing out the one with all the S's and the and so forth that were not necessary. So we apply that. We end up with the diagonals are all these alpha minus E. So 1, 2, 3, 4. And then we get a beta for the ones that are nearest neighbors. Notice this is not nearest neighbor. So this would be say the third carbon. So this is the first carbon, second carbon, third carbon, fourth carbon. The third and fourth carbon don't interact, so we get zeros in those cases. So at the second carbon, it interacts with the first and the third, and so we get betas, and so you can see the structure that you get for this determinant. Now this is a 4x4 determinant, and as I said, you can solve this, and actually, in this case, because there are so many of these elements are zero, this is actually a relatively easy 4x4 determinant to solve. And page 336 there's like an example problem on page 336 and 337 that shows exactly how to solve this, okay? And so you'll get 4 solutions, and if you look that up, you'll see how they did this. You get 4 solutions, 2 of them are alpha plus or minus, so the plus is the lower energy, minus being the higher energy, 1.62 times beta, and then you get the 2 solutions that are plus or minus 0.62 beta. Okay, so those are our 4 solutions. So if we were to order them in a kind of MO diagram, so the lowest, because that's the largest beta, the lowest energy is this, this molecular orbital that has something like this shape, which I've tried to make in ChemDraw. And then the next highest would be the plus, so right, these are all attractive interactions. And then now we get into this point where we're negative, where we're starting to get nodes. So here is our plus where we have reads these two carbon overlap, 2 carbon overlap, 2 carbon overlap, 2 carbon overlap. And in this case, we have 2 nodes. And in the top one, the alpha minus 1.62, we have 3 nodes between all of the carbons. All of them are in different, all the p orbitals are different signs. And so you can see our highest occupied, we put our 4 electrons, and then our highest occupied molecular orbital is this one, right? And our lowest unoccupied molecular orbital would be this one. So if we were to predict some chemistry based on HOMO to LUMO interactions, we would use these 2 here. And so we have our 4 electrons, we plug them in to get our pi electron binding energy, and we got 2 in here, 2 in here, we add that up, we got 4 alpha plus 4.48 beta. Okay, which once again is just multiples of integrals that we really can't solve at this point. But we can compare this to, if we looked at an ethylene is an isolated pi bond, no delocalization, right? Because there's just that one pi bond. So if we were to just put 2 ethynes together or 2 ethylenes together, those would be localized pi bonds, right? And if we did that, remember the energy of the ethene was 2 alpha plus 2 beta. Put 2 of them together, we get 4 alpha plus 4 beta, right? And notice this is larger than this. And so the excess that we calculate based on this is our delocalization energy. So we get 0.48 extra beta because we're allowing these because these pi orbitals interact over multiple carbon centers. Okay, and so that shows you kind of the favorability of delocalization, and the Huckel theory does a good job of approximating that. So the next one we're going to do, but we're going to do it in one of our Zoom meetings, is the cyclic structure of benzene. So until we get to that part,